Okay, and welcome back to episode 6, if I've counted properly. I'm afraid I'm going to have to take a second and remind myself where I got up to, because the last stream ended slightly earlier than I planned. So where do we want to go? Let's go to our project we're working on. Let's make a new Tmux session for it. What do we do? We've made and populated a vertex buffer. Cool. So that kind of gets us to the end, believe it or not, of the bit that I was more confident on, which if you happen to have seen any of the previous streams might be a little concerning, because they haven't been the smoothest sailing. But we've created our kind of basic resources. We've got everything that we need in place. We're doing something super simple and just have these hard-coded corners, which I think makes a clockwise winding triangle facing the camera. And we have all of that set up. Sorry, wrong with buttons. So that in here, we are copying that data into our renderer, or into our buffer on the GPU. And so we're now ready, I think, to actually start on the graphics pipeline. And this is the part I remember feeling like spooky magic whilst going through the tutorial. There was just a lot of options and variables, and obviously the tutorial does what it's meant to do, and it tells you what the right choice for each of them is, and it gives you a little explainer. But it really just bounced straight out of my head. So we are going to try again. I'm going to assume people haven't watched the previous streams because there's a lot of content there. The way we're approaching this is we're going to start in the spec. I've not got a particularly good picture in my head of what to do, so I'm going to start at just graphics pipeline. We're going to make a graphics pipeline, discover all the things we're missing, and then backfill from there. If we hit a point in that where we're just super stuck, we don't know what to do, depending on the problem, we'll either refer back to a previous project that I've done following tutorials to try and work out a set of values that would work and try to understand the problem, or we'll refer back to the original tutorial that I actually used, which is the VK tutorial. One detail, if you are interested and you want to try this yourself, the VK tutorial uses the old Vulkan 1.0 style render passes, unless they've updated it. Which we saw in the spec has been deprecated as of 1.4. I think if you search instead for VK Guide, there's also, I guess, a more modern Vulkan tutorial that maybe Luna G, I think, maintains. So if you are looking for a way to learn this yourself, I would advise following that and not following me. I'm not sure what I hope people take out of this. Maybe just entertainment. Yeah. So, we are going to need the spec. I think after the last stream, I did have a quick browse for, and there is an entire chapter on pipelines. There we go. Let me just check on the stream. I think I might want my code slightly bigger. Does that look readable? Yeah, let's hope so. And it might be worth us taking a minute to actually read some of this, because I'm not sure what is going to be new to me and what isn't. So, the following figure, which is this kind of terrifying diagram down here, shows a block diagram of the Vulkan pipelines. Some Vulkan commands specify geometric objects to be drawn or computational work to be performed, while others specify state controlling how objects are handled by the various pipeline stages, or control data transfer between memory organizers, images, and buffers. Commands are effectively sent through a processing pipeline, either a graphics pipeline, ray tracing pipeline, or compute pipeline. So we're going to want a graphics pipeline. The graphics pipeline can be operated in two modes, either as a primitive shading or mesh shading pipeline. Primitive shading, the first stage of the graphics pipeline, the input assembler, assembles vertices to form geometric primitives such as points, lines, and triangles based on a requested primitive topology. In the next stage, the vertex shader, vertices, can be transformed, computing positions and attributes for each vertex. And then if tessellation geometry shaders are supported, they can then generate multiple primitives from a single input primitive, possibly changing the primitive topology or generating additional attribute data in the process. So for what we're going to be doing in our kind of 2D kind of quad texturing plan that I've got in my head, we will not be using tessellation geometry shaders. So we will have an input assembler that will read in triangles, and we will then write a very simple vertex shader that, what will it even do? I guess we'll take those triangles in and pass sensible things through to our fragment shader. Is this stuff here useful? So cluster culling shading. When using the cluster culling shader, a compute-like shader will perform cluster-based culling. A set of new built-in output variables are used to express visible cluster. In addition, a new built-in function is used to emit these variables from the cluster culling shader to the input assembler. I don't know what that means. I don't think we need it. When using the mesh shading pipeline, input primitives are not assembled implicitly but explicitly through a mesh shader, which again I don't think we're doing, so I think we can skip over that. And then common, the final resulting primitives are clipped to a clip volume in preparation for the next stage, rasterization. The rasterizer produces a series of fragments associated with a region of the frame buffer from a two-dimensional description of a point, line segment, or triangle. These fragments are processed by fragment operations to determine whether generated values will be written to the frame buffer. Fragment shading determines the values to be written to frame buffer attachments. Frame buffer operations then read and write frame buffer operations then read and write the color and depth or stencil attachments of the frame buffer for a given subpass of a render pass instance. The attachments can be used as input attachments in the fragment shader in a later subpass of the same render pass. Again, I think kind of over my head. It looks like there's an entire section about fragment shading, and was there one about vertex shaders? There is. Okay, so we might need to jump to them. The compute pipeline is a separate pipeline from the graphics pipeline, which operates on 1, 2, or 3-dimensional workgroups, which can read from and write to buffer and image memory. So we're not doing a compute pipeline at this point, so we don't need that. What else? This ordering is meant only as a tool for describing Vulkan, not as a strict rule for how Vulkan is implemented, and we present it only as a means to organize the various operations of the pipelines. Actual ordering guarantees between pipeline stages are explained in detail in the synchronization chapter. Okay. And then we have the terrifying diagram. So, what I take from this is, over here is how the compute pipelines work. And you can see they're super simple, right? They just have the one bit where they do their job. Which makes sense, I guess. There's less assumptions you can make about what work will be done in a compute shader because they're so generic. This, I assume, is what it was telling us about using a mesh shader. I know nothing about it, so I'm going to skip straight past that. We're really interested in this chunk over here on the left. So this dark grey is our resources. And this on the very left is kind of the steps available to us in a graphics pipeline. Hopefully we can ignore most of this. So I think the input assembler we will need to set up so it can read in our vertex buffer. In the future, we'll probably need an index buffer as well. But for now, we'll read in from our vertex buffer, and it knows to read those values in as triangles, and it will pass those values through to our vertex shader. Which, will we be using any of these? We have uniform buffers, sampled images. So yeah, by the time we get to like texturing our quads, we're going to have values in here. And when we want to do things. So if you were doing things a kind of more normal way, where you had your model stuck somewhere on the GPU, and then each frame you're sending just, kind of like skeletal translations and rotations, so you can, move the arm on a model. You would be using things like uniform buffers and push constants, which you can see appear in here. I won't talk too much about them because I don't really understand them too well. But that would be our vertex shader, which we'll then head on through. We will then ignore everything up until the fragment shader, which is where we say what color this outputted piece will be. So I guess the vertex shader will read in these triangles. it will go through these other steps that we're not really touching. And then the rasterization step, I think, if I understand it right, takes our triangles and it associates those triangles with pixels that will appear on the screen. And then each of those areas of the screen that are considered to be kind of part of one contiguous thing will be our inputs into the fragment shader, which will determine what color the actual pixels end up being. So, what is all of this down here? Each pipeline is controlled by a monolithic object created from a description of all the shader stages and any relevant fixed function stages. So those fixed function stages being things like the input assembler, I guess. Linking the whole pipeline together allows the optimization of shaders based on their inputs and outputs and eliminates expensive draw time state validation. A pipeline object is bound to the current state using VK command bind pipeline. So we will create a pipeline. This is what this is saying. We first create a pipeline that describes that full, what will the right thing be? Like that full set of steps that we're going to go through. And then we call this command to say, when I submit this buffer, I would like to make use of this pipeline, if that makes sense. What are these things? If the command buffer inheritance feature is not enabled, then no state, including dynamic state, is inherited from one command buffer to another. If the command buffer inheritance feature is enabled, then all graphics and compute state that is valid at the end of the command buffer executed in a queue is inherited and valid at the beginning of the command buffer next executed in the same queue. This applies to both primary and secondary command buffers, where a primary command buffer submitted to a queue will inherit state from the previously submitted command buffer to that queue. Secondary command buffers will inherit state from the primary or secondary command buffer they are executed in. And after a secondard command buffer is executed, its state inherited by the primary or secondary command buffer that executed it. Command buffers executed in a queue do not inherit state from any command buffers executed in another queue. Cool. I don't know exactly what we're going to do with that information, but we will see. I think this is one of those places where I don't think it all makes sense for us to pause and try to understand every step, because I think we're just never going to get done. So I think what we'll do instead is we're going to just keep ploughing, take the bits we need, and backfill until we have a triangle drawn. So what do we have here then? So multiple pipeline creation, I don't think we need. So we're going to make one pipeline. Compute pipelines, we don't need, but I am curious about. So let's have a quick read. So compute pipelines consist of a single static compute shader stage and the pipeline layout. The compute pipeline represents a compute shader and is created by calling create compute pipelines with a module and name selecting an entry point from the shader module, where that entry point defines a valid compute shader in the VK pipeline shader stage create info structure. Okay, cool. So if we look at this, it has the logical device that owns it, a pipeline cache, which can be null if we're not using caching, up to however many create infos we're going to pass in, and then a list of those, allocator, and a pointer of pipelines to hold them. Cool. And then down here, what does it take? It takes flags, stage, layout, base pipeline handle, and index. An index to the p create infos parameter to use as a pipeline to derive from. Cool. I don't know what that means. I'm guessing this layout maybe says what. Oh no, here, shader stage create info. Okay, I don't understand what that means, and that doesn't bode well, because I think these are substantially simpler than the graphics pipelines. So I think we risk confusing ourselves if we spend too long looking at them. So let's jump ahead. Graphics pipelines consist of multiple shader stages, multiple fixed function pipeline stages, and a pipeline layout. To create a graphics pipeline, you call this thing. I guess let's add a pipeline to our renderer state. So we're in here, and let's say graphics pipeline will be AVK pipeline. Do we care that they make multiple? I think we can just make the one, and we'll extend it later if we need a slice of them, but let's hope not. Let's then jump all the way down here, and we'll say in here, create graphics pipeline. So you will generate a result, so it can fail. I'm going to call create graphics pipeline. There isn't a singular one? No. So we'll do this where it takes a renderer device. We're going to have no cache, just to make life simple. Create info count, we will have 1, and we will have to pass in our create info, which doesn't exist yet. We have nil for our allocator because we're not using a custom allocator, and we can pass in our pipelines, which will be renderer dot what do I call it? Graphics pipeline. Why does it not like this nil? Cannot convert type untyped value nil to pipeline cache. So it's not a pointer, it's just a value. Can we jump in here and see what actually is a pipeline cache? It's a non-dispatchable handle, which is a distinct U64. So I think options, we can pass a 0, or we can pass, this is our kind of like, what would the right word be? Our kind of generic nil value in Odin. So if the thing takes a 0, it will be a 0. If it's a pointer, it will be nil. If it's a boolean, it's false. I think, you know, it just kind of coerces to whatever it needs to be. So I think we'll do that to make it clear. It's not a 0 because we care it's 0. It's just the nil value. And then create info doesn't exist yet. So let's come up here and we'll make our graphics pipeline create info. You're going to take an S type because everyone does. Graphics pipeline create info. Let's see down here. Is any of this useful? Just realised it might not actually be that easy to follow me reading things, because I think the text is quite small and there's just a lot of words on screen. So what I might do, if I do this, shall I highlight things as I'm reading them? Does that help? Just looking at the stream to see if that's any more visible. Maybe. Okay. So we're here. So the VK graphics pipeline create info structure includes an array of pipeline shader stage create info structures for each of the desired active shader stages, as well as creation info for all relevant fixed function stages and a pipeline layout. Pipelines are created and returned as described in that thing that we skimmed over that we might need to go back and read, but let's see. So there we go. This is what I remember being a pain. There's just a lot of information in here, right? We're kind of getting into the real guts of it here. So S-type we've already got. P next we're going to ignore until we need it. Flags, I'd be interested to see. Allow derivatives, create derivative, create view index from device index, dispatch base, fail on pipeline, compile required. I don't know what any of these things do. So I'm going to just set none of them, because none of those early ones sound like what we need. I will put an empty flags there, so I remember that there is a flags thing that I'm not setting anything in, so if we have issues later, I can at least come back and think about that. Stages and stage count. It's probably the first point we're going to have to actually step away and do something else, isn't it? So number of entries in the stages array, and stages is a pointer to an array of pipeline shader stage create info structures describing the set of shader stages to be included in the graphics pipeline. So I'm guessing this is going to be 2. All right, I'm guessing we're going to have is 2. And I'm guessing that because I'm thinking it's going to be vertex and fragment shader. So let's stick a to do there, because this is probably the first point to go and jump away and do something else. I might just quickly read what the rest of these are, in case there's another thing that's easier for us to go and do. So, vertex input state is a pointer to a pipeline vertex input state create info structure. Ignored if the pipeline includes a mesh shader stage, which ours won't. Can be null if the pipeline is created with the dynamic state vertex input extension, which ours won't be. So we will need that. So let's put our to-dos together. An input assembly state is a pointer to an input assembly state create info structure, which determines input assembly behavior for vertex shading, as described in drawing commands. We're not enabling that extension, which would let it be null. It is ignored if the pipeline includes a mesh shader, so we're going to need that as well. Input assembly state. Tessellation state. Defining the tessellation state used by tessellation shaders. I'm hoping we can set to null because we're not going to have a tessellation shader. Maybe that's naive. Viewport state is a pointer to a VK pipeline viewport state create info. Can be null if the pipeline is created with both dynamic state viewport with count and VK dynamic state scissor with count dynamic states. Do we want to do that? So I think the Vulkan tutorial does make those dynamic state. I'm kind of curious what it looks like if we don't. So let's come in here. So I guess the downside to making it not dynamic state is we will have to recreate this pipeline, but we can just pull this out into a function at the point that we need that. If it's not clear, at this point we've not got any handling for the fact that the window may change size. So currently it would crash, I think, if the window changed size mid-drawing. So we're going to have a bunch of stuff to come back and work out related to that. I think this is one of those things, because we'll have to update the size of our viewport to match the updated extent when the window changes size. The rasterization state is a pointer to a rasterization state create info structure defining rasterization state. It is not going to be done dynamically, which means we need to do it. So rasterization state. I'm enjoying the SpongeBob casing we got there. Should we just do that one? The multi-sample state. Might be a really simple one, because I think we're going to not have multi-sampling if we're going to go for this kind of retro pixelated sort of look. Instead of having it, I think multi-sampling is what we do when you have like anti-aliasing. So pixels that are really kind of between two pixels get a like a linearly interpolated value that looks like it's a mix of the pixels around it. I think we're going to do our sort of nearest neighbour colour in that case, just because it's one less thing to think about. So that one might be really simple, but we probably need it anyway. The depth stencil state, defining the depth stencil state to use when rasterization is enabled. For depth or stencil attachments accessed during rendering. I think we don't need, because I don't think we're going to have a depth stencil. At least not in the first version of it. A color blend state is a pointer to a structure defining color blend state. It can be null if it's dynamic. I think. You know, let's put them all in. And we'll have a bit of a read. So we've got a color blend state. P dynamic state is a pointer defining which properties of the pipeline state are dynamic and can be changed independently of the pipeline state. We're going to aim for none. We're gonna try and just do it. And if we have pain, then I guess we'll come back and revisit that decision. But let's see. Layout. Layout is the description of binding locations used by both the pipeline and descriptor sets used with the pipeline. If device properties API version is greater than or equal to 1.3, layout must not be accessed outside the duration of the command this structure is passed to. Wonder what that's about. Okay. Going to trust that the validation layers would catch us if we were doing that. We're going to still need a render pass, which is a handle to a render pass object describing the environment in which the pipeline will be used. The pipeline must only be used with a render pass instance compatible with the one provided. Excuse me? The pipeline must only be used with a render pass instance compatible with the one provided. See render pass compatibility for information. The implementation must not access this object outside of the duration of the command that this structure is passed to. So when it says the implementation, I think that means drivers. In fact, did it say the same thing up here? Okay, no, so that is us. But I think when it says the implementation must not do something, it means that drivers mustn't do things. Subpass, the index of the subpass in the render pass where this pipeline will be used. I'm hoping that's just 0. Type is subpass. Because it's not a subpass, it's just the pass. Base pipeline handle and base pipeline index. The parameters base pipeline handle and base pipeline index are described in more detail in pipeline derivatives. I'm going to hope we don't need them. If any shader stage fails to compile, the compile log will be reported back to the application and VK error invalid shader NV will be generated. Okay, so we might actually have to go and write our shaders at this point. The state required for a graphics pipeline is divided into vertex input state, pre-rasterization shader state, fragment shader state, and fragment output state. Okay. Are these things that we've already mentioned over here? The vertex input state and the input assembly state. Yes. Okay, so the vertex input state is defined by these things. If this pipeline specifies pre-rasterization state either directly or by including it as a pipeline library and its P stages includes a vertex shader, this state must be specified to create a complete graphics pipeline. What does complete graphics pipeline link to? What page are we on? 826. A complete graphics pipeline always includes pre-rasterization shader state with other subsets included depending on that state as specified in the above sections. The hell is this? Oh, okay, it's further down. Okay, ignoring that for now then. So, where am I looking? In here. If a pipeline includes graphics pipeline library vertex input interface bit extension in the flags, either explicitly or as a default, and either the conditions requiring this state for a complete graphics pipeline are met, or this pipeline does not specify pre-rasterization state in any way, the pipeline must specify this state directly. Don't know what that means. Okay. Let's go through these one at a time then. Should we start with stages? So stages is a pointer of these things. Any information about them? Nothing before it, so there's no preamble to read. Pipeline shader stage create info is defined as all of this stuff, where we have flags to say what stage it is, and a shader module, where a shader module is kind of the resource you create that owns your compiled shader code. Cool. I'm going to go quickly sketch out. So in here, these are gone. Draw a triangle is still a goal. What do we need to do? We need to write simple vertex and fragment shaders. I'm going to create shader modules for them. And then we will create pipeline shader stages. Then in here, do the rest of the graphics pipeline. Cool. Cool. Are we having fun yet? I might give this a read, and then I think we need to take a detour and go write some GLSL. I'm not even sure if I've got GLSLC installed. Have a look. GLSLC. I might have installed. Okay, cool. We do have it installed. Where do I have it installed? Ah, you get it with the Vulkan SDK. Okay, that's nice. That's good to know. So, pipeline shader stage create. Ah, fucking Ocular has frozen again. Okay, we're on page 798. Can I close it? Come on. Can't even close it. I thought that would show me Ocular in there somewhere. Yeah, it's crashed, isn't it? Okay. Let's come back. I guess we'll just launch it again and hope. Not sure why it did this last time as well, which is weird because I've never had any trouble with Ocular. But maybe it's the curse of we always talk at work about like the demo curse. The moment you want to show something to someone, it breaks. I guess maybe this is the streaming curse. Okay. So pipeline shader stage create info has a type, a pnext, flags, stage, which specifies a single pipeline stage, module, which is an object containing the shader code for the stage. Pname is a pointer to a null terminated UTF-8 string specifying the entry point name of the shader for this stage. So I guess we're going to call that main. So you make one of these per shader module, do you? What's specialization info? Okay. So I don't think we're going to need any of this outside of making the graphics pipeline. So what do we want to do? Pipeline shader stage create info. Can we say vertex shader stage create info? Which will be a VK what am I looking for? Pipeline shader stage create info, which will have an S type. Pipeline shader stage create info. P-next we're going to ignore. Flags is possibly interesting. So flags, it won't tell me what type flags is. So let's come back to here. And we see pipeline shader stage create flag bits. Create allow varying subgroup size, require full subgroups, allow varying for the extensions and another extension. Okay, we're going to assume we're good with default behaviors and ignore all of that. Stage is vertex. Module will be our vertex shader module that we'll need to make. Name, I'm going to go with main. And specialization info. What are you? Which map constant IDs to offsets in P data, data size. Each structure contains a specialization info member, which can be null to indicate no specialization constants. So let's let's do that. We'll just leave it because everything gets zero initialized. Unknown field name, because it's P name, which knows it's a C string, so that's good. Why are you unhappy? Because you're actually a set of flags, not a single flag. So now we need to go and make our shader module. So vertex shader module, which will be a VK shader module. Cool. How do we make a shader module? To create a shader module, call VK create shader module. Okay. What section are we in now? Chapter 9. Shaders. All about shaders. Okay. So shader modules contain shader code and one or more entry points. Shaders are selected from a shader module by specifying an entry point as part of pipeline creation. The stages of a pipeline can use shaders that come from different modules. The shader code defining a shader module must be in the SPIR-V format as described by this appendix. So this is some intermediate representation that means we can use any shader language we like as long as we can compile it to SPIR-V. I have not dabbled very much with shaders, so I've used GLSL just because it's what the tutorial I was following used. We're probably going to have to just go and rip their code because I don't remember how to write a shader myself. Maybe in the future we'll come back and get really proficient with GLSL, but there is so much to do before we're really able to dabble with shaders in a fun way. So we are going to need to call create shader module for a VK device, VK shader module create info, allocator and shader module. Okay. I guess we just do that then. Do we want this to live on our render state? Because I'm just thinking, if we're not having any dynamic state on our graphics pipeline, we're going to want in the future to be able to tear it down and build it again. And if we don't put the shader module on our render state, we'll have to pull it in again, which just feels like unnecessary fuss. So I'm going to come up here and I'm going to make a vertex shader module just to hold on to it. So we do it once and then we've got hold of it. If we want to use it again, we can use it again. Right. So in here, we're going to create our vertex shader module. And then down here, this complains because that doesn't exist yet. But we'll be able to do that. And it would currently error because it doesn't have anything in it yet, but it will compile. And so inside of this, we're going to call this function. It returns a result. So it could fail. Create shader module, which will take a device. It will take a, a create info. We don't have a custom allocator, and we point it at our slot in memory that we want it to go into, which is our vertex shader module. If res not equal to success, then we panic. How do we do this? Panic. Failed to create vertex shader module. Failed to create vertex shader module. We need to define the create info, which is a VK. No, not vertex. What's it going to be called? Shader module create info. Yes. S type will be shader module create info. Like that. And if we skim down, hopefully it's just down here. P next, we hope to not need. Flags is reserved for future use. Code size is the size in bytes of the code pointed to by pcode, and pcode is a pointer to the code that is used to create the shader module. Type and format of the code is determined from the content of the memory addressed by pcode. Okay, so we're going to need to. So in here we have a to-do. Code size is something, and pcode. You can just come in here and do that for now. So we've got a lot of to-dos cropping up. What do we need to do here then? We need to read in our compiled shader code, compiled vertex shader code, and get size and pointer to its data. Okay. One thing I'm not sure of is kind of, I guess, how the life cycle of these things works. So, does this copy from this place? So when I create the shader module, I'm assuming it must copy this data onto the graphics card, or it must copy it to somewhere that is in graphics card visible memory. It isn't just going to use this pointer, I'd assume, but I don't know that for sure. And then we have the call to destroy it. Can be destroyed by pipelines created using its shaders are still in use. Which I think backs up what I'm saying, right? It's, we create the shader module, it will copy the data it needs over, and the shader module now owns that. Which means that whatever memory we allocate in this context here, we can then free. If we were doing this as part of our state, so if down here we made this, then we created our pipeline, we could then immediately destroy the module. But if we're going to keep a handle to it in state, then I think what it means is actually we need to destroy it down here when we're actually like de-initting or uninitializing, there we go, the entire renderer, because otherwise what we're doing, otherwise we wouldn't be able to refer back to it, right? We're making some long-lasting state. Which may be a problem. We might be making it more complicated than it needs to be, but we're doing it for now. Then shader module identifiers. I don't know what that's about, so we're going to ignore it. Okay. I'm going to take a brief break. I will be back in a minute. Let me just stick a nice big next on here so I don't forget what I'm up to. Let's make it really hard to miss. Cool. I'll be back in 1 minute to crack on with that. Okay, and I am back. So, we want to read in our compiled shader code. That will require that we go back and write some shaders. How do we want to go about doing this? Does it live in main? I'm going to make it over here. And we're going to end up with a vertex shader and a fragment shader. So let's write that. However, I did mention before that I'm not really very good at writing shaders, as in I don't remember it at all. So I think this might be a point where we go and just rip something really simple from the Vulkan tutorial. GLSL is really similar to C, I think deliberately so. And so I'm hoping we can't use this one because they're hard coding their stuff into there. And then out color, they're using some numbers. Eich. So what are we going to want? I guess after the point they've got vertex buffers. So if we're in this one, I think, do they provide their shader code in? I think there's some links in here somewhere to like the full code. This one has a lot of chat on it. There we go, vertex shader, fragment shader. This looks more promising. Yeah, so you can see the fragment shader is kind of as simple as it can be. It specifies the GLSL version, and then we tell it that we're going to pass it in a vec3, so 3 floats, to use its color. We're going to pass out a vec4, which is the color we actually want applied to this fragment, and then it makes them all opaque. And our input, I think if I've defined vertex up here as a position and a color, somewhere we're going to have to define a struct that tells, you know, the graphics card that what we're passing in has a vec2 in position 0 and a vec3 in location 1, and then those will line up with this, and the input assembler will be able to take in each vertex and pass these into our shader like we want. And then GL position is just one of those things that we have to go and learn if we're going to write more GLSL. I think it has a set of variables that are sort of special variables. I guess what this one is saying is it's setting a position state based on our vertices that we've passed in, because obviously we know that in position means position. We need to tell the graphics pipeline that. So I think we can just take those basically unchanged. So let's jump back. So we have hash version 450. We're going to have a layout. Location is 0. In position, it's not Odin, so we do need to remember that it does need semicolons. Then we're going to have a layout. Christ. Location equals 1, which will be our color. I'm going to confuse myself if I insist on using the English spelling of color. I'm going to keep doing it stubbornly, but we will see. We're going to have a out variable, which is our color that we're passing to the fragment shader. And then our inch point main, which is GL position vec4 in position, and a frag color will be our in color. So hopefully it's reasonably clear what that's doing just from naming and the sort of similarity to C. One thing that is cool is this, where the GLSL vector types are very kind of like ergonomically designed. Clearly, if you're doing this, you're going to be writing a lot of vectors and slotting vectors together into different shapes. So a vec4, you can pass in 4 floats. You can replace any 2 of those that are next to each other with a vec2. And if I remember right, I think it has very nice like swizzle operations. So you could do like in position dot yx to flip the 2 around and things like that. So all this is doing is our vec4 is xy. We're setting z to 0, and I think w. I'm trying to remember what that actually means, and I can't remember. So I'm going to worry about that later. We set the value to 1 for all of our points. So basically, we're only meaningfully describing them in the xy plane. So we'll set that one up, and we'll also steal their fragment shader quickly. 450 layout. Location is 0. Will be an in vec3. Frag color. I'm guessing the name doesn't necessarily have to match up, but for sanity, it seems like it should. I think it's the location that it uses to actually find it, not the name that we give it. We make our void main entry point, and we'll just pass through that our out color. And again, similar nice vector stuff. We can say in here we want the RGB values from our value we pass in, and we set the alpha channel to always be opaque. Did I format this one? I did not, so let's format that too. Cool. So I guess we now have a bit of a moment of truth. If I come into shaders, can I compile them? What do you actually do? You have options and a list of files. Preprocess, compile, assemble. Outputs only the results of the pre-processing step. I would like to know if I can set the name. I would call that option O. Lovely. Right, output to file. A file name of dash represents standard output. What actually is the standard then? So if I go glslc and I just say main.vert, it gives me a.spv. So let's kill that. If I instead do the same command but tick O vert.spv, I get vert.spv. And if I do tick O, frag.spv, main.frag, it will give me that. Cool. Cool. What do we want to do then? We are going to end up having to rerun those relatively often. So we might want to consider making like a simple make file or something, so we can do like make build, make clean. Maybe we do that in a little bit though. Let me remove my spv files and cd back to here. It might be worth us adding .spv to our gitignore though before I forget. Gitignore star.spv, because otherwise we're going to end up committing our compile outputs. Okay, let's do it manually for now. Do I want the outputs to live inside of the shaders directory? I might not for now. I'm just have them live at the root. So I'll do glslc tick o vert.spv shaders main vert and glslc tick o frag spv main.frag. So they now exist in there. They do not appear in my untracked files. And if I come back into here, I will put at the very top a couple of constants. So I would like to have my vertex shader path will be vert spv, and this fragment shader path will be frag spv. So we'll zip back down to our to-dos, down here, and we're going to need to do some work to actually pull that data in, which I think will involve the OS package, but let's go check. So Odin, OS package, purple, because we've been here before. And I'm hoping it just has a read file. Read full? Read entire file? Read full. File descriptor and a buffer. Read entire file from file name. Has an allocator, which is a good sign, I guess. Will return us out a slice, and that slice will have both the length and the pointer we need. What does or error do? Error will report us a useful error if it fails. And what values does error have? General error, IO error, sys Windows system error. So I think maybe we do this and we print the error and crash if we fail. Because this is one of those things we very well might fail, right? As we refactor and move things around, we end up not pointing at a file that exists, for example. Yes. So skim back down to here. What do we want to do? We want to do you return us out data and error. So let's do data and error will be equal to OS read entire file from file name or and you take just a file name, string. It has a default allocator. That's what this lock is about, but it has a default value, so we're going to ignore it. And in this case, we would like to pass in our vertex shader path. We're going to say here if not equal to nil, format eprint line error reading vertex shader file, and then panic. Failed to read vertex shader file. Just slightly redundant, but what are you going to do? Let's run, my god, Odin, run main. Validation error. And then a seg fault, but this didn't fail. Alright, so if I say in here else, format, print line, hello, we should see that hello come out. And we do. So, we know for a fact that that worked. So we now have data, and we can now say in here that our code size is data dot A. It's a slice of bytes. You have to do len data. Is that the way you do it? And then this one will be a raw data. Which is angry. Cannot assign value raw data of type pointer to U8 to a pointer U32 in structure literal. Can I just cast you arbitrarily? Please. And hope that it works. pcreate infos stages is null, which is a validation failure later. Cool. That looks like it worked. So I think we now need to do the same again, but for a fragment shader, right? So let's come in here and say fragment shader module, which is another shader module, and just jump down back to here. We're going to do all of this. Is it worth the effort to pull this out into another function? They're both really simple, so I'm going to, not for now. As this gets more complicated and we have, assuming this grows in a direction where we have more shaders being added, we might want to. But I just want as few things that could go wrong as possible. And dodgy abstractions of systems I don't understand very well feels like it will make that less likely not... Sorry, makes it more likely that things will go wrong unexpectedly, not more... The bad one. I'm speaking rubbish, but I mean the right thing. So if it errors, we will print standard error, error reading fragment shader file. We output the error, and we'll panic with fail to read fragment shader. In here, we want our second create info for a shader module like that, and we will make it a shader module create info. Code size is the length of data, and p code is the raw data in data. Now, I really hope that we don't end up in trouble with this casting it to U32. It's one of those places, I don't know if there's something where, like, the operating system is little endian and it's going to mangle these U32s, because they're not really U32s, they're a bunch of U8s, but I'm going to hope that the GLSLC compiled files are exactly what we want, and we're just going to shunt them through. But if it does fail and fall over, that would be a good place to come back to. Hey? Where'd that go wrong? Okay, my result is I'm going to make another shader module for the device, if I could only type. It's create info and renderer dot fragment shader module. And if it fails, then we panic. We'll run it quickly. Validation error in the create pipelines stage, which is fine because we know that that's not done yet. So we skim down here. No, that is still to do because we've not actually created the stages. We have a pipeline shader stage create info. We're going to have a fragment shader stage create info, which is pipeline shader stage create info. Where this type is all of this stuff. Flags is empty, and your stage is going to be fragment. Our module will be renderer dot fragment shader. And again, we're going to make all of these just say main. Have a quick sip of tea, if you'll excuse me. Nice. So, we can now make a stages. What's the type on you? Pipeline shader stage. So let's come back up here and make pipeline shader stages, which will be a slice. Can I do that to make it in further type? No. Okay. Can I just do it like this and then get it to in further type? We're vertex, shader, stage, create info, and fragment. Oops. Back to there. Fragment, shader, stage, create info. And it's angry because it doesn't know what type you are. Yeah. So let's make you a slice of VK pipeline shader stage create info, which means that you actually can be the length of pipeline shader stages, and you can be raw data pipeline shader stages. I'm going to complain it's the wrong type, so we cast to a U32. And that's the first chunk done. So our graphics pipeline is now aware of these two shader stages, and it has access to the shader code. Right. but it doesn't yet know the layout of the of these things. So that's still to do, but progress. Let's jump back to here. I'm going to put a / next and do a work in progress commit, just because I'm a bit of an airhead and could very easily mess this up from here. So what have we done? Work in progress toward graphics pipeline. Very nice. I think the next thing to do will be this stuff about our input assembly and vertex input state. Which means we want to jump back to create graphics pipeline info. Let's see. Do we care which one we do first? A pointer to a vertex input state create info structure. Let's see you up here. Vertex input description. Applications specify vertex input attribute and vertex input binding descriptions as part of graphics pipeline creation by setting this pointer to a input state create info structure. Alternatively, if the graphics pipeline is created using a dynamic thing, then the vertex input attribute and vertex input binding descriptions are specified dynamically, and the pointer is ignored. Pipeline vertex input state create infrastructure has S-type, has pnext, it has some flags that we want to look at, and then we have binding description count, binding descriptions, and attribute description count and attribute descriptions. Now, I can't remember what bindings are and what attributes are. Hopefully it will explain for us as we go. So we have in here our shader stages. We would like now, what is this called? Vertex input state. So let's go vertex input state create info. So I think that's the type of this. Sorry, type of this. Panics, because that's not real code. That's not real code yet. Ugh, fucking... I do need to sort out, at some point, maybe it would be a good stream if we get bored of doing Vulkan bits. My NeoVim setup is janky and terrible. I think I started a rewrite at some point, because I think a Mason version bump broke a load of stuff, and I was like, I don't need Mason, I'll set it up myself, and I've clearly done a terrible job. But I don't know, I always find tinkering my configs just boring enough that I don't want to go and do it, whereas this is boring in a way that I do want to do. So vertex input state create info vk, let's basically say that again. Pipeline vertex input when people say Vulkan is verbose, they mean it. So it needs to have an S-type or it just won't know what to do with it. That S-type is pipeline vertex input state create info. Pnext we're going to ignore until we're forced to use it. Flags we will make empty for now. Oh, we're going to make empty forever because it has no actual values yet. Vertex binding description count, vertex binding descriptions, vertex attribute description count, and vertex attribute descriptions are things we're going to have to go and work out. I do think, so these are very directly related to this type here. And so I'm kind of wondering if we might want to just pull that into another file. So we're about to add a load of logic that's related strictly to that. Yeah, let's do that. So let's pull you out and we'll make vertex.odin. Do I tell you what package you're in? Is that why that's complaining? That's also because it's got no imports. Import. Can't remember what it was. It was core / math. Sorry, core math. linalg glsl. And I think we're going to want to make things in here that are like our vertex binding descriptions and vertex description attribute descriptions even. So let's have a look. Vertex binding description. Each vertex input binding is specified by the VK vertex input binding description structure, defined as this thing, where binding is the binding number that this structure describes, stride is the byte stride between consecutive elements within the buffer, and input rate, value specifying whether vertex attribute addressing is a function of the vertex index or of the instance index. I do not understand what that means. Vertex attribute addressing is a function of the instance index. Attribute description. So this is the other thing. So we have input binding description and we have input attribute description. We have a location, which I'm imagining will line up with these locations, right? Like we have these. Format is the size and type of the vertex attribute data. Offset is a byte offset of this attribute relative to the start of the thing. Right. So can I say here then that my vertex input attribute descriptions will be a slice of VK vertex input attribute descriptions, where the first one it doesn't know about Vulkan because I've not imported it. Maybe there was an error pulling this out. Vulkan. So we do that. Do you now know what type you are? What if I put a dot there? No. So VK vertex input. Why did that get wiped out? Interesting. It just doesn't have any autofilling. Okay. My rubbish LSP bites again. I'm not even sure we need this. I'm going to delete that and see if it will compile without it. Oh, you don't have an S-type. So we're going to have a location. I think we can make it 0. Binding is the binding number for which this attribute takes its data from. And that is this thing up here. Christ, I do not understand what this is talking about. So we have a vertex input binding description. Ah. Do we have one of these for each type of object that we want in our vertex input? Okay, so hang on. So if I have vertex input binding description, it's a VK vertex input binding description. Binding is the binding number this structure describes. It says make you a binding 0. Stride is the byte stride between consecutive elements within the buffer. Can you be a stride of size of vertex? Is that how this works? And then input rate, I think will have to be like this, because we're not using instancing. So what we're telling it is, what are we telling it? That when it reads in the vertex buffer, that each block of data of size of vertex corresponds to a single vertex. And then this attributes thing, binding number which this attribute takes data from. I'm going to say the bindings are going to be all 0. Expected an operand. Is that because I've refused to put? I'd really like it if I could get the LSP to do me some auto filling. So you're a VK format, the size and type of the vertex attribute data. Okay, so we'll say here to do format. Ah, that's why it's not doing it. I have typoed. And that is why I wanted it to help. It's not helping that much. Okay. So we'll work out what to do with the format. And the offset is a byte offset of this attribute relative to the start of an element in the vertex input binding. I think that Odin has a built-in like offset of. Let's do a quick check. Can we do Odin lang offset? Yeah, offset of. Does it mention it in the overview, does it? Okay, it doesn't mention it in here. I'm reasonably sure I remember there being a built-in offset of. So I think we can say in here, offset equals offset of, and then I can't remember if I want a type. Expected 1 got 0. Guessing it's something like the type and then the name of the field. Expect an identifier for field argument. Is it the other way around? Okay. Let's try and Google more effectively. What was this offset of? This guy is seeing an error. Current behavior. Failure. Proc. Offset of demo and see. Ah, it's not a string, it's a identifier. No? Cannot assign uint pointer. To a U32. Why are you getting a pointer? I thought you would get me a size of it. Odin Lang. Struct layout, I guess. Create struct packing and how to match C. Do you have anything like what I'm expecting? How to use using in a struct. Structure field tags. Okay, so you don't say anything about it. In fact, is there a package built in here? Offset in bytes with the struct of the field. The offset of selector or offset of member. Returns a uint pointer. Okay. So I think uint pointer isn't a pointer, it's a unsigned integer the size of pointers on this system. And so it's complaining that it can't automatically coerce that to a U32, is it? Is that what it's saying? Yeah. So if I just cast it forcibly to a U32, it will say it's fine. Let's hope that that's fine. How can we check it's fine? Can I go into main and right at the tippy top, I would like to do format, print line, vertex, input attribute descriptions, get the first one, dot offset, and I expect that to be 0. So ignore all the validation layers. Yeah, we get 0. And we expected to get 0 because we're grabbing the first field. We'll worry about what to make our format in a second. But in this one now, we come in here and we tell it that the location is going to be 1. I'm going to say that the binding is 0. I need to tell it what format it's going to get. But importantly, offset is a cast to U32 offset of vertex color. And it's in bytes. Vec2 is 2 F32, so 2 4-byte floats. So I'm expecting to see 8 in here. Format, print line, vertex, input, attribute, descriptions, 1, offset. We run it, we ignore all of the validation errors, and we see 8. Okay, so that is doing what I want. And this did say I want the offset in bytes, not bits. There's a byte offset relative to the start element. Cool. What on earth do we do for format? VK format. Okay, we need to tell it what we're actually giving it. I don't actually know what the right answer there is. So we're in here. Location equals 0, binding is 0, format. Cannot assign format a type. I'm hoping that, in fact, Odin has the nice stuff where it can work out what one of these actually is. I think we want to say we're float 32s, so we are what are we passing in? 2 F32s. So is it R32, S float, G32, S float? So I think what we want here is R32, G32, underscore S float. Maybe. And this one is going to be R32, G32, B32, S float. If we run that, we do compile, and we fall over when we create this thing, which is fine because we haven't finished it yet. I think that's what that needs to do. Can you tell I'm not very confident? Sorry, let me have another sip of tea. Voice is going on me again. Okay. So where does that get us up to? I guess we now want to go back to our vertex input state create info. Input state create info. And I think we pass these values in. So flags is empty. Vertex binding description count is the length of vertex binding. I've only got one. Let's hope that's right. P vertex binding descriptions is a pointer to vertex binding description. And then vertex attribute description count is the length of vertex attribute descriptions, and the pointer to vertex attribute descriptions is the raw data vertex input attribute descriptions. This one is angry because it is not a U32, so we will cast it to U32. And hopefully that's this one. Vertex input state. It might actually take a pointer. Yeah, it does. So we pass in a pointer to that thing. Oh, dearie me. Okay. If I run that, we still fail here. Create infos of our assembly input state is not there. So That's fine. It's falling over at a point that we know we've not done a thing. I was kind of hoping to see if this had something just terribly obviously wrong with it, it would tell us. So I'm going to take that as a good sign it doesn't. Again, possibly naive. I don't think they cover that much stuff. But let's just keep plodding along. At some point, we're going to try and draw a triangle and get a black screen, and then we can painfully step back through all of this, but that's my best guess. Which means the next thing to do is our input. No. We've done that. We've done that. To dynamically set it, call this thing, which we're not doing. Where can we find this input assembly? I was kind of hoping it would just be just underneath this. It doesn't look like it is. Damn it. How do we find it again then? Where's our chapter about pipelines? We're making a graphics pipeline. In our graphics pipeline, we're going to need the create info. Inside that create info, we have our input assembly state. So we jump to here, and we can work on that next. It's hopefully simple, because our topology needs to be triangles. I think that is the long and short of this. So let's make an input assembly state create info. Which will be a VK pipeline input assembly state create info with an S type of pipeline input assembly state create info. P next we're going to hopefully not need. Flags is not needed. Topology. I think it's a triangle list. Let's see. So topology is a VK primitive topology, defining the primitive topology as described below. Primitive restart enable controls whether a special vertex index value is treated as restarting the assembly of primitives. This enable only applies to indexed draws, and the special index value is either the maximum value when the index type parameter of Vulkan 1.4. Oh, sorry. Primitive restart is not allowed for list topologies, which is what we're using. Okay. Restarting the assembly of primitives discards the most recent index values if those elements formed an incomplete primitive, and restarts the primitive assembly using the subsequent indices, but only assembling the immediately following element through the end of the originally specified elements. The primitive restart index value comparison is performed before adding the vertex offset. Okay, I think we can just leave that false. Primitive topologies determines how consecutive vertices are organized into primitives and determines the type of primitive that is used at the beginning of the graphics pipeline. The effective topology for later stages of the pipeline is altered by tessellation or geometry shading if either is in use. Depends on the execution modes of those shaders. In the case of mesh shading, the only effective topology is defined by the execution mode of the mesh shader. Primitive topologies defined by this thing are all of these, and I think we have a triangle list. So when the primitive topology is VK primitive topology triangle list, each consecutive set of 3 vertices defines a single triangle primitive according to this equation. The number of primitives generated is equal to that. Provoking vertex mode. I don't know what provoking vertex means to us here. I'm not even sure where that comes up. But this is what we're saying. We want it to pass in 3 vertices, and we want our graphics pipeline to treat that as a triangle primitive. So I think that's an easy one. Quick win. Input assembly state. Create info. Righty then. Graphics pipeline, create info. Vertex input state. Input assembly state. Tessellation state can be null if the pipeline is created with that thing set. I'm going to hope we can just leave it null because we're not doing one. Viewport state is a pointer to a VK pipeline viewport state create info struct. Defining viewport state used when rasterization is enabled. Can be null if you've made it dynamic. Let's give that a look. So what do we have? Viewport. Is viewport one word? Viewport state create info VK viewport pipeline viewport state. Create info. Fill in this boring one. So pipeline viewport state create info. Nice. What's the other fields? What are the other fields even? So pnext, we're going to hope to not need. Flags is reserved for future use. Viewport count is the number of viewports used by the pipeline, which will be a single viewport. So viewport count will be 1. We need a pointer to viewports. And a pointer to scissor. I wonder if we can just put those on our renderer. Is that silly? So what do we currently have on the renderer? So our viewport, I think, will have an extent on it. Surface capabilities, current extent is what determines our swap chain create info. Image extent. And if I jump into viewport, we will see that it has a width and a height. And an X and a Y. The viewport's upper left corner. Despite the names, min depth can be less than, equal to, or greater than max depth. That's confusing. What's all this saying? Viewport parameters shown in the above equations are found from these values, OX and OY. What is O? Command set viewport. Why am I struggling to think what we do with this? So I think viewport basically needs to just match the image extent. So we're going to want our width and height to be pulled off our image extent. And I guess X and Y will be -1, -1. X and Y, the viewport's upper left corner, X, Y. and or is it 0, 0? It's one of those things that's irritating. I can't ever remember what the coordinate systems for all these things are. I think we always talk about the screen as being like from -1 to 1. In fact, it would tell me if these are uint. They're not, they're floats. So they can be negative. Is there anything in here about... Well, valid usage might tell me, actually. Valid usage of a VK viewport. Width must be greater than 0. Where am I looking? Maintenance 1. Native viewport height is not enabled. Absolute height must be less than or equal to the physical limits. Viewport bounds range. What is viewport's bound range? So if a render pass transform is enabled, the values px, py, and ox, oy defining the viewport are transformed as described in the render pass transform before participating in the viewport transform. The application can specify a negative term for height, which has the effect of negating the y coordinate in clip space before performing the transform. When using a negative height, the application should also adjust the y value to point to the lower left corner of the viewport instead of the upper left corner. Using the negative height allows the application to avoid having to negate the Y component of the position output from the last pre-rasterization shader stage. Width and height of the implementation-dependent maximum viewport dimensions must be greater than or equal to the width and height of the largest image which can be created and attached to a frame buffer. So they must be at least as large as our images. Which makes sense. Is there like a diagram in here somewhere that says like what our coordinate system is? When it says the upper left corner, is that 0, 0? Or is that -1, 1? Controlling the viewport. Render pass transform. Coordinate transformations. We are feeling thoroughly out of our depth at the minute. Clipping shader outputs. Is that what the scissor does? We have to define what our scissor is. So I think what we have is we have the simplest possible thing where we want to have a viewport that fills the entire screen, and then scissor I think just defines what things will be clipped, and we're going to make the scissor fill the entire screen as well, so we're not clipping anything that would fill on the screen. Primitive clipping. There's a whole load of variables getting used, and I'm really hoping to find something somewhere that'll just say, here's a diagram showing you what a viewport looks like and what the coordinate systems we're using are. Begin transform feedback. Classic Vulkan fashion, there's a whole load of extensions. Vertex post-processing. Pre-rasterization shader stages. Following fixed function operations are applied to vertices of the resulting primitives. Well, that didn't seem to say anything directly useful. Is there anything if I look for coordinates? Coordinate operation, coordinate transformations. I mean, maybe this says what they are? Sorry, I'm mumbling to myself now. To clip coordinates for a vertex result from shader execution which yields a vertex coordinate position. Perspective division yields normalized device coordinates in a vertex If a vertex in clip coordinates has a position given by x, y, z, and w, then the vertex's normalized device coordinates. Yeah, this is that thing I was saying. I don't really remember what this W is used for. It's to do with perspective. Render pass transform can be enabled for render pass instances. What is this saying? When render pass transform is enabled, the following features are enabled. Each viewport will have its width, height, and its center 0, 0, similarly transformed by the implementation. The scissors will also be transformed. Okay, so the viewport transformation is determined by the selected viewport's width and height in pixels, as well as its depth range, min and max, determining a depth range scale value and a depth range bias value. The frame buffer coordinates are given by these. Multiple viewports can be supported. What are x and y? The vertex's frame buffer coordinates have limited precision where the number of fractional bits retained is specified by this thing. Pipeline viewport state create info. Hey, is that where we are? I go back and find where I've got a viewport. Pipeline viewport state create info. So we've gone full circle. Oh, I'm not convinced I understand that any better than I did at the outset. Let me just have a look here. Because offset. What is offset? Is offset the thing we were looking at? So on viewport. Multi-viewport is not what we're doing. Viewport count and scissor count. The X and Y members of offset member of any elements of pieces must be greater than or equal to 0. Evaluation. Okay. So that makes it sound like the offset is 0 means the top left corner. Oh, both not dynamic. The counts must be identical, which makes sense. If the graphics pipeline is being created with it dynamic, pipeline viewport state create info. So viewport count. So the scissors offset must be greater than or equal to 0. There's nothing about the XY on viewport that I can see. P scissors, viewport count, scissor count. P next. I mean, does this one have anything about the viewport XY? Because I'm assuming they work the same way. If they don't, viewport count must be greater than 0. Then we have set scissor. So this is if we're going to do it dynamically. Okay. I'm going to guess that the scissors and viewports use the same coordinate system, and that this rule therefore applies to the viewport as well, but that's another thing that could be wrong. Okay. So, what is it we need to know? We need to know the extent of the screen. So let me call it a surface extent. I think there's a rect 2D struct. And somewhere in here, what are we actually doing at this point in here? Creating the swap chain. So the point we're creating the swap chain, inside of all of this, we are grabbing our surface capabilities current extent. So if instead of doing that, I say my renderer dot surface extent is at this point equal to surface capabilities current extent, and then inside of this we can use the renderer surface extent unhappy rect 2D to extent 2D. Why is extent 2D different than rect 2D? So extent 2D just has a width and a height. A rect will presumably have an offset on it, where offset is a X and a Y. Cool. Cool. Interesting that they're ints. Is that interesting? At least if they're in pixel values, maybe it's not that interesting. Still unhappy because surface capabilities is not defined here. It's defined down there. Surface capabilities. So if we do that, that gives us our extent. And then much further down, we can create our viewport. So viewport will be a VK viewport. I think X and Y will be 0. I think width will be renderer dot surface extent dot width. No. F32s cannot assign value of type F32. Sorry, of type U32 to F32. Okay, I think the viewport may have broken me. I think we're gonna have to go check what the Vulkan tutorial says about it. Because I could take a best guess, but I also think we're just digging a hole. Where would we find that? Would it be under drawing? Under rendering and presentation, maybe? Oh my god, what's it called? Viewport? No, it's not under there. Graphics pipeline? Render passes, maybe? Where, oh where? Where'd it go? Maybe fixed functions. Yeah, viewports and scissors. A viewport basically describes the region of the frame buffer that the output will be rendered to. This will almost always be 0, 0, and width height. And we just cast it to a float. Min 0, max 1. Remember that the size of the swap chain and its images may differ from the width and height of the window. The swap chain images will be used as frame buffers later on, so we should stick to their size. The min depth and max depth values specify the range of depth values to use for the frame buffer. These values must be in the range from 0 to 1, but min depth may be higher than max depth. If you aren't doing anything special, stick to 0 and 1. Okay, so as confusing as that all was, I think we did have the right answer. And that answer is we just cast these to floats. Which surface extent dot height. And that thing it's saying about the swap chain image size could be different from the window size. I don't really understand, because we've got this, we're setting this just before we pass that size into our swap chain image, I think. Right, if I go search for surface extent again. Oops, surface extent. So here, the image extent is that value. And so the two can drift, because if you resize the image, there will be a point where the two are different. But what I'm imagining is we will detect that somehow, and then we'll rerun this to create the swap chain again, and we would reset this value. We would have to recreate our graphics pipeline, and then that's the value we want it set to. So I think that's all feeling logical. And then I think our min depth and max depth was going to be 0 and 1. So we have a viewport like this, and we're going to have a pointer to viewports, and viewport like so. And then I think up here, let's also have our scissor. Probably a VK. I think scissor didn't have its own type, did it? I think scissor was just a... Was it a rect 2D? Yeah, rect 2D. Rect 2D, which will have on it an offset and a extent. Our offset, I think, can be an X0, Y0. Our extent, I think, is the same as that thing up there. So we're going to have a width, which is a U32 again. What a weird little corner this is. So I think U... In fact, because that's an extent, I think we can just pass it in. Right, renderer dot surface extent, and then our scissors down nya can be a pointer to scissor. Okay, which means that here U can be a pointer to viewport state create info. Check it compiles. We expect validation errors. Dynamic rendering. Create info's render path is null, which is fine because we've not made it yet. Layout we've not made yet. Multi-sample state is null. Rasterization state is null. So we've got a few more things to set, but we are getting there. Okay. I'm going to take another short break here. I think we're making good progress though. Let me stick in my little next reminder again, because otherwise I will forget. Add a load of lines to make it nice and easy to get back to. Grand. Alright, I will be 1 minute. Okay, and I am back. Where were we up to? We've got at least 4 more of these to do. And then we should have a graphics pipeline. Rasterization state. Should we keep going in order? So, can we go back and find our graphics pipeline create info thing again? Pipelines, graphics pipeline. Scroll, scroll, scroll. Pipeline create info. Rasterization state. Oh, you have so many things on you. Okay. So let's come into here. We want a rasterization state. Create info is a VK pipeline rasterization state create info. S type is, as always, exactly what it sounds like it would be. Rasterization state create info. P next we hopefully don't need. Flags is not needed. And then let's look down this list. Depth clamp enable. Controls whether to clamp the fragment's depth values as described in depth test. If the pipeline is not created with this extension present, then enabling depth clamp will also disable clipping primitives to Z-planes of the frustum as described in primitive clipping. I guess we'll just disable it. Yeah, it's a boolean, so we can just disable it. Rasterizer discard enable controls where the primitives are discarded immediately before the rasterization stage. Where the primitives are discarded. What on earth does that mean? Polygon mode. This one I think is useful because, yeah, if we are debugging things later and stuff isn't looking like we expect, we can turn it to line to give us kind of a wireframe version of our thing, or point to just see all the dots for the corners. Oopsie daisy. But we will want fill, I think. So polygon mode, fill. Where the primitives are discarded immediately before the rasterization stage. I don't know what that means or does. I'm going to just leave it. It'll be false by default. Hopefully that doesn't bite us. Cull, we're going to cull the backs. Apparently this one will need to be a set, I guess. Nice. And then front face, we need to tell it how we're defining front and back. I think we did clockwise. We come back and look at this. So we've got bottom left, top middle, bottom right. So yeah, clockwise. This is one of those that if we go to render it and we see nothing, we can flip that and just check. Depth bias enable controls whether to bias fragment depth values. Depth bias constant factor is a scalar factor controlling the constant depth value added to each fragment. Depth bias clamp is the maximum or minimum depth bias of a fragment. So I'm assuming if we don't enable it, all these depth bias things don't matter. Line width is the width of rasterized line segments. So valid usage. If depth clamp is not enabled, depth clamp enable must be false. Polygon mode must be fill. Fill mode. Fill rectangle extension, I don't know what that is. Is there anything about what value that line thing takes? The width of rasterized line segments. Where's the next mention? Command set line width is the width of rasterized line segments. Sets the width for subsequent drawing commands when it's created with that value being dynamic. If wide lines feature is not enabled, line width must be 1. Sick. We're going to assume that's true for us too and bung that in there. Painful that it doesn't seem to mention it up here, but it feels like a safe bet that it's the same as what you get on the dynamic version, right? And so hopefully we now come down to nya, and you can be a rasterization state create info. It still blows up. Create infos, we've got no render pass, no layout, no multi-sample state. But we are getting there. We're getting somewhere. Okay. Multi-sample state is hopefully going to be super duper easy because we are not enabling it. So we jump to you. It has a whole bunch of fields on it. Pipeline, multi-sample, state, create, info, and up here, multi-sample, state, create, info, which will be a VK pipeline, multi-sample, state create info. S type is pipeline multi sample state create info. Which is not auto-completing, to be really irritating. Pipeline multi sample state create info. Pnext and flags we don't need. Rasterization samples. I'm hoping I can just tell it that one of these is false and then we don't use it. Rasterization samples is a sample count flag bits, specifying the number of samples used in rasterization. This value is ignored for the purpose of setting the number of samples used in rasterization if the pipeline is created with dynamic state. But if it is not set, it is still used to define the size of the sample mask array. Sample shading enable can be used to enable sample shading. So if I just set this to false, can I just ignore everything else? Sample shading can be used to specify a minimum number of unique samples to process for each fragment. If sample shading is enabled, an implementation must invoke the fragment shader at least this many times per fragment. If sample shading enabled is true, sample shading is enabled. So in here, we would like to say sample shading enable is false. And then hopefully all the other values simply don't matter. Interestingly, that now doesn't flame out like it did before. Rasterization samples parameter. Rasterization samples is 0. Must be a valid VK sample count flag bits value. Okay. So if a fragment shader entry point statically uses an input variable decorated with a built-in of sample ID or sample position, sample shading is enabled and a value of 1 is used instead of min sample shading. If a fragment shader entry point statically uses an input variable decorated with sample, sorry. Oh dear. Where am I looking? Then sample shading may be enabled and a value of 1 will be used instead of min sample shading. I think that's all not us. So it's unhappy about our rasterization samples. So I guess rasterization samples we just make 1. Because it must be greater than 0. Rasterization samples will be 1. Unhappy. To sample count flags. Oh, okay. It's a... yeah. Is that what it wants? Create info doesn't have a render pass, doesn't have a layout. Cool. But it now does have that thing. Right. Where is our pipeline creation thing? Compute pipelines. Multiple pipeline creation. Is this a really silly way of getting there? Okay, I'm border scrolling. Let's go sidebar, graphics pipelines. That was more sensible. And then it's just under here. We have rasterization state, multi-sample state. Depth stencil state is a pointer to this thing, defining these used when rasterization is enabled for depth or stencil attachments accessed during rendering. We're not accessing any, so I think we can maybe skip it. Or at least we can skip it for now. Color blend state. When rasterization is enabled for any color attachments accessed during rendering. I think we're going to want to enable that eventually. But maybe just for the sake of getting a thing drawn first, we're going to disable it. What is this saying? The frame buffer. Blending combines the incoming source fragment's RGBA values with the destination RGBA values of each sample stored in the frame buffer at the fragment's location. Right. Yeah, so I remember this not being trivial. In the previous project I did, where we're drawing quads for sprites essentially, we have to enable this in the end to get to a place where we can draw one quad over the background and have the transparent pixels actually be transparent. But as you can see, there's a bunch of stuff in here. I think it's one to come back to when we when we need to. What does logic op enable? Whether to apply logical operations. It's not about the whole thing. Included in the blend state create info structure during graphics pipeline creation. So I think we can just not pass it in. Pipeline, color blend state create flags, unless one of these is disabled, but it doesn't. The pipeline color blend attachment state structure. Blend enable controls whether or not blending is enabled for the corresponding color attachment. So yeah, when we make our color attachment, we'll just have to disable blending for now. Since we're going to want to come back to it, I might put it back in here and just make it explicitly nil, so that when I inevitably do a grep for blend, I can find it quickly and know this is a place that needs updating. Layout and render pass may also be big. Let's go have a look. So, where am I looking? Layout is the description of binding locations used by both the pipeline and descriptor sets used with the pipeline. If physical device properties API version is greater than or equal to Vulkan 1.3, layout must not be accessed outside of the duration of the command this structure is passed to. And render pass is a handle to the render pass object describing the environment in which the pipeline will be used. The pipeline must only be used with a render pass instance compatible with the one provided. Okay. Home straight. Where's my type for layout? Is there a thing in here I can click? There is not. Layout is of type VK pipeline layout. That's annoying. You're gonna make me just do a search for it, are you? Let's just try and scroll and see. So dynamic state, complete graphics pipelines, graphics pipeline library layouts. If different subsets are linked together with pipeline layouts created with this extension, the final effective pipeline layout is effectively the union of the linked pipeline layouts. Sounds like not us. Please, something in here linked to layout. Can I just do a quick Control F and see if it comes up? Hey. So, pipeline layouts in Chapter 14, Resource Descriptors, about descriptor sets. Access to descriptor sets from a pipeline is accomplished through a pipeline layout. 0 or more descriptor set layouts and 0 or more push constant ranges are combined to form a pipeline layout object describing the complete set of resources that can be accessed by a pipeline. The pipeline layout represents a sequence of descriptor sets, with each having a specific layout. This sequence of layouts is used to determine the interface between shader stages and shader resources. Each pipeline is created using a pipeline layout. To create a pipeline layout, you call this thing, which has an allocator and a pointer, and our create info has set layouts, which references descriptor sets and push constants. Right. What descriptor sets are we going to need? I guess we're going to need them for the images that we're writing to when we do our present at the end, maybe? Yeah, sorry, let me just check because I can hear my phone buzzing. And it's buzzing to tell me that I need to wrap things up. So, I think we're going to come back and do pipeline layouts next time. I might save myself a little note though. So next to do, this is 14.2.2 in the spec. So I guess next time we'll have a look at creating a pipeline layout, which will also require us having a bit of a look at descriptor sets, which we haven't actually had to touch at all yet. The descriptor set layout is defined by an array of 0 or more descriptor bindings. So we might actually have to spend a bit of time going back and reading these resource chapters. I'm not entirely sure what we need. So we'll call that good. Hard to know if this was all actually correct because we can't actually see anything yet. But it's compiling. And so it could be worse. So what do we have? Untracked main vertex.odin. Could we move that file? So what have we done here? Work in progress toward graphics pipeline. Cool. I think that might be the end for today. So thank you for joining. I hope you've enjoyed, and I'll catch you again next time to hopefully actually see a triangle.